All right, let's talk about building code that lasts. Today, we're diving into the solid principles. Think of them as your guide to writing software that's not just functional, but clean, robust, and honestly, a real joy to work with.
But before we get into the nuts and bolts, let's start with a question I'm sure every single one of us is asked at some point. Why does good code go bad? You know the feeling, right? You start a project, it's beautiful, it's clean, and then a few months later, it's this tangled mess that you're afraid to even touch. Well, that's what we call code rot, and Solid is basically the cure.
So here's what we've got on deck. We'll kick things off with why solid even matters. Then we'll walk through each letter, S, O, L, and I, which we'll tackle together, and then D. And we'll wrap it all up by showing how these ideas lead to a super important pattern called dependency injection.
All right, first up, why should you even care about these principles? Well, they're not some lofty academic idea. These principles, which were really popularized by Robert C. Martin, you probably know him as Uncle Bob, are just super practical, road-tested guidelines. They help us answer those fundamental questions, like how should I structure this class? And how should these different pieces of my code interact?
And the payoff for following them is huge. I mean, obviously, your code gets less complex, easier to read, that's a given. But for me, the real magic is in the last 2 points here. Extensibility, that's the ability to add new features without setting the whole house on fire. And loose coupling, that's the holy grail. It means your different modules aren't all tangled up like a bowl of spaghetti. They can be worked on, tested, and changed independently.
Okay, let's get into the first one. S, the single responsibility principle. This one's pretty simple on the surface, but it's so fundamental. It's all about keeping your classes focused and preventing them from turning into those massive God objects that try to do everything.
The rule of thumb is right here. A class should have only one reason to change. What does that actually mean? It means if you have to open up a file and modify a class, you should be doing it for one specific purpose. If you're changing it because the business logic changed and also because the database schema changed, well, that's a big warning sign. Your class has more than one job.
I love this analogy. A class that does too much is like a Swiss Army knife. Yeah, it's kind of cool that it has a dozen different tools, but let's be honest, when you just need a screwdriver, you'd rather have a proper screwdriver, right? It's the same with our code. It's way better to have a collection of sharp focus tools, or classes, than one clunky thing that does everything poorly.
So here's a perfect example. On the left, you've got this report class. Its job is to handle the report's content, and its job is to save that report to a file. See the problem? 2 different reasons to change it. The solution is just so elegant. On the right, we just split it. We have one class that knows about the report's data and a completely separate report persistence class that knows how to save things. Each has one job. Much, much better.
All right, moving on to O for the open/closed principle. Now this one is a real game changer. It's all about how we can add new functionality to our systems without breaking the stuff that already works.
So the official line is that software should be open for extension but closed for modification. That might sound a little weird at first. How can something be open and closed? Well, it means we should be able to extend a system's behavior, add new features without modifying its existing already tested code. You add new code, you don't change old code. And the best way to think about this is your phone, right? You add new capabilities to it all the time by installing new apps. That's extension. What you don't do is take a soldering iron and rewire the phone's motherboard every time you want to play a new game. That would be modification. We want our code to be like the phone, not the motherboard.
Let's look at a classic code smell. On the left, we've got a payment processor with a massive chain of if-else statements. One for credit cards, one for PayPal, one for crypto. Every time you need to add a new payment type, you have to come back here and modify this file. It's brittle. The solution, and this is so idiomatic in Go, is to use an interface. On the right, our processor just accepts anything that implements a payment method interface. Now we can add new payment types all day long, and we never ever have to touch the payment processor code again. It's closed for modification, but open for extension.
Okay, now we're going to group 2 principles together, L and I, because they're really 2 sides of the same coin. They're both about designing good, clean interfaces. And since Go is all about interfaces, this is super important stuff. We're talking about the Liskov substitution principle and the interface segregation principle.
First up, Liskov substitution. Sounds complicated, but the idea is simple. If some type S is a subtype of type T, then you should be able to replace T with S anywhere in your program without things blowing up. The classic example is the rectangle and square problem.
If a function expects a rectangle and you pass it a square subclass, that function shouldn't break. If setting the height of your rectangle also secretly changes its width because it's actually a square, you violated the contract. Your subtype has to behave like its parent type promised it would.
And that brings us to the interface segregation principle, which is basically, don't create fat interfaces. A client, meaning a piece of code that uses an interface, shouldn't be forced to depend on methods it doesn't actually use. Think about it. If you have a big worker interface that has methods for work and eat, what happens when you have a robot worker? You're forcing your poor robot to have an eat method that does what? Nothing? It's awkward and misleading.
So what's the solution? It's simple, and it's the big takeaway for both of these principles. Prefer many small, specific interfaces over one big, general-purpose one. Instead of that one fat worker interface, you create a workable interface and a feedable one. Your human worker can implement both. Your robot worker only needs to implement workable. It's clean, it's precise, and everyone knows exactly what contract they need to fulfill. Okay, we've arrived at our final principle, the D in Solid. This is the dependency inversion principle, and honestly, this one might be the most powerful of them all. It completely changes how we think about connecting the big picture parts of our application to the nitty-gritty details.
The principle says this: high-level modules should not depend on low-level modules. Both should depend on abstractions. Okay, let's translate that. Your important business logic, the high-level stuff, shouldn't care how you save data to a database or how you send an email. That's low-level detail. Instead, both your business logic and your database code should depend on an abstraction, which in Go almost always means an interface.
So this is what we don't want. Our high-level notification service knows exactly about the low-level email sender. That arrow shows a direct dependency. They're tightly coupled. So what happens when your boss says, hey, we need to send SMS notifications now too? You have to go crack open the notification service and start changing things. It's inflexible and a pain to test. And here's the magic. We invert the dependency. Look at the arrows now. We stick an abstraction, an interface, let's call it message sender, right in the middle. Now the high-level notification service depends on the interface, and the low-level email sender also depends on the interface because it implements it. They don't depend on each other anymore. The direction of the dependency has been inverted, flowing towards the abstraction. This is decoupling at its finest.
So you might be thinking, okay, that inversion diagram looks great, but how do I actually do that in my code? Well, the answer is a pattern called dependency injection, or DI. This is the how. It's the technique we use to make dependency inversion a reality.
DI is a form of a broader concept called inversion of control. It sounds fancy, but it just means this. Instead of an object creating its own dependencies, like a car object building its own wheels, those dependencies are created somewhere else and are given to it or injected into it from the outside. We've inverted the control of who is responsible for creating the wheels. And why do we go to all this trouble? The benefits are just fantastic. Yeah, it decouples things and makes your code more flexible, but the number one reason every senior engineer I know loves DI is for testing. Because you're injecting the dependencies, in your tests you can just inject a fake database or a mock email sender. This lets you test your business logic in complete isolation without needing a real database or a network connection. It's an absolute game changer for writing reliable code.
So we've gone from S all the way to D, covering single jobs, open extensions, smart interfaces, and inverting dependencies. It's a lot, I know, but it all boils down to this final question for you. Think about the project you're working on right now. Which one of these principles jumps out at you? Which one could you use tomorrow to make your code just a little bit better? Because that's the whole point, taking these ideas and putting them into practice.